right, so let's move on to our next speaker, and that is Arushi Nath, and she'll speak to us about photometric observations of the Didymos Asteroid System before the impact. Go ahead, Arushi.
Hi, everyone. It's great to be presenting again at the Royal Astronomical Society of Canada monthly meetings. So my name's Arushi Nath, and I'm a grade 8 student from here in Toronto. And as you all probably know, recently, around a week ago, the DART mission impacted the binary system Didymos. So today I'll be talking a bit about my own photometric observations of the system before the impact. So just a quick overview of the NASA's DART mission. The DART mission is a planetary defense test, which means, just to clarify, that neither Dimorphos, Didymos, or any other asteroid right now has a threat to hit the Earth. So the goal of this mission was to impact the Didymos binary system. So that includes the main asteroid, Didymos, which has a diameter of around 800 meters, and the moonlet, Dimorphos, which has a diameter of 140 meters. So the goal was to crash into the moonlet to change the orbital path of this asteroid. So it was able to successfully impact the moonlet, but this is not the only part of the mission. It has 3 other main steps. The first step is to cause around a 73-second change in the orbital period of the moonlet. Second, it's also essential that we get the binary period with an uncertainty of 7.3 seconds or less. And third, this is also a test to see how efficient the impact was, to see if in the future there's an actual asteroid that has a threat to impact the Earth. Then we'll know exactly what size of impactor to send to the asteroid. So many people have been observing this asteroid, citizen scientists, of course, but also lots of professional observers from all around the world. For example, in Chile, there's the Atlas telescope, which is also in South Africa. And in Australia, there's the Las Cumbres Observatory telescope. And but there's also citizen scientists who are also measuring the system. And citizen scientists are scientists who have either telescopes in their backyards, or maybe are getting proposals for limited time on other people's telescopes. So as you can see on the 4 pictures below, there's 3 main observations of the Didymos system. So first is the pre-impact observations, because it's very essential to get a baseline reading of the orbital period of the asteroid. The second is right after the impact, all the debris which is scattering around the asteroid, and it's forming tails. So while stacking the images, as you can see in the first 3 pictures, you can observe 3 tails coming from the asteroid. And finally, once all the debris has scattered, that's the actual test to measure if the orbital period of the asteroid system has changed. So how do we measure the photometry of asteroids? So telescopes have a CCD camera attached to them, and this is receiving the light from the sky. And the more light it receives, the higher brightness a pixel becomes. And by combining all of these brightness pixels, we're able to get the total brightness of an object, in this case, Didymos. So now let me just show you a short animation of the Didymos binary system. So as you can see right here, the moonlet is going behind the main asteroid, which is why you can see a smaller dip right here. And now very soon, the moonlet is going to go in front of the asteroid, as it just did, and that's where a bigger dip just happened. And this dip is also caused by the shadow which is coming on the asteroid. So About the asteroid light curves, they can reveal three main things about the mutual events of the two objects in the Didymos system. First, the primary occultation, which is when the moonlet, so the secondary object, is passing in front of the main asteroid. The secondary occultation is when the bigger object, Didymos, is passing in front of the moonlet. And finally, the primary eclipse is when the shadow of the moonlet is going in front of Didymos and it's masking some part of the asteroid. But light curves can also reveal the orbital parameters of the asteroid. Especially in this case, this asteroid is not completely circular, and this is because the mass is not enough that it can keep heavy enough gravitational pull to keep the asteroid in a circular way. Um, so just to show easier, I have an example of the asteroid. It's a potato, but let's assume it's the asteroid. So the light curve of the orbital period is caused when the asteroid is rotating around. So as you can see right now, only this part is visible. So that's when the dip in the light curve comes along. And now as the asteroid slowly rotates, more of the asteroid is visible, which means more of it is reflecting light, which means the brightness of the asteroid will go up. And similarly, when it goes back to facing like this, the light will go down again. And the orbital period of Didymos is 2.26 hours. So now I'm going to talk you through the 7 steps that I took to get the photometry of this asteroid. So the first step was getting images from the telescope. The second step was preprocessing and the data. Third was plate solving and aligning. Fourth was getting the aperture radius for both the COM stars and the target asteroid, sorry. Fifth was finding comparison stars that actually worked for my purposes. Sixth was removing phase angle and offsets, contributions, and finally was generating the light curves. So let's start off with my telescopes. So I've been able to get access to five telescopes located in Australia and Chile. And they have apertures ranging from 0.4 meters up to 2 meters. And to get access to these telescopes, I had to either write a proposal or get a membership, which gave me some limited amount of time on the telescopes. So to plan exactly when I would observe the telescopes, observe the asteroid, I've started taking observations since March 7th, actually. And to make sure Didymos is in my frame, I have been using some visibility calculators that are available, and that's to make sure that the air mass is low enough while I'm taking my observations. And also to create my observations, I had to input many informations, like my exposure time, the filters I wanted to use, the binning, and so on. And on the bottom right, you'll be able to see a small animation of one of my observations I got. This is on the 24th of September with a telescope located in Chile. So you can see here the asteroid is moving from the center of the image all the way to the far corner. So now step 2. So I was getting hundreds of images from these telescopes, and each image has a FITS header where it stores important metadata from the observation. So this could include stuff about the telescope specifications, like its focal length and aperture, also the observatory location, the time the observation was taken, and the exact coordinates that it was pointing to in the sky. And all these information is very useful when doing the further analysis of these images. So now let's go on to step 3, which is when I was plate solving my images. So lots of steps that I've done here can also be replicated in Python. I've shown an example here while plate solving, which is what I did in Python. For more information on how I did that, you can see my previous RASP presentation at the RASP General Assembly 2022. And that's how I talked about including plate solving and observation. So now let's go on to the fourth step. So this is selecting a good aperture radius for both the asteroid Didymos and the comparison stars. So I had to select different size apertures for both the target star and the comparison stars. And it was quite a challenge to actually get the correct size of the aperture because either if it's too small, then it won't cover the whole asteroid or the whole object. But if it's too big, then it'll also cover a lot of noise from the image. So I had to find the balance in between the two, which took a lot of trial and error. So step 5 was finding suitable comparison stars to use because not all of them that were in the image I was actually able to use. Some examples of ones I was not able to use, you can see in the first graph here right on the left. The magnitude is very scattered, and this is because the star was either too big or too small to be viewed in that aperture radius. In the second one, you can see that the brightness is changing over time for some reason. It could change, and then that means that it won't be a suitable comparison star. And then finally, you can see on the bottom left, this is a suitable comparison star because the magnitude is constant over the whole observation time. And if you look on the right, this figure here, I stuck it around 4 to 7 comparison stars each observation. And in this graph, you can see on the y-axis is the actual magnitude of these stars. And on the x-axis is the magnitude computed by the camera. So there's a blue line here, which signals the best comparison stars to use based on this to make sure that the actual magnitude is corresponding with the magnitude that the instrument detected. So I was getting a lot of observations of the Didymos, lots of them on different nights. So while combining them, it was important to take in a couple things into account. One of them is the position phase angle, because the phase angle is basically the angle in between the sun, the asteroid, and the Earth. So since that is changing, the brightness of the Didymos asteroid will also be changing. And also, since the Didymos asteroid was coming towards us during this impact, it was getting brighter and brighter every day. So I had to take that into account, which is why I applied the phase angle and offsets to my data set. So in the first picture here, this is without any extra things added. And in the second figure, you can see this is where I've applied the phase angle and offset. And you will notice that they all seem much more aligned than in the first figure. So this comes to my final step. So this is actually generating the light curves of the Didymos system. So in the first graph, you can see this is one of my observations of about 1.8 hours. But as I said before, I was getting many nights of data, and that's where I combined them. So in the second figure, you can see both my observations combined. But 2 observations was not enough, which is why I've been working with 2 other astronomers, Daniel and Joaquin. And in total, we all got 6 observations. And combining all these observations together, I was able to get a light curve of 2.599 hours. And the expected light curve is 2.6 hours. So that was very accurate. And I was also able to get an amplitude of around 0.114. And this was great because with 1 week of data, 6 days, we were able to get a pretty accurate light curve. A couple of days ago, I found about this source, which gave me all the mutual events of the Didymos system. So you can see them here. In black is the ones before the impact, and in red are the ones after the dark mission impact. So I hadn't noticed it before, but one of the observations actually fell in line with one of the mutual events, which is why in this figure here, you can see the 7th observation right here in blue is going slightly, is not lining exactly with the other observations. And this is because of the change, because we were experiencing one of the mutual events. And this is also why, after aligning it with the orbital period, they were all able to come together. So since the orbital period of this asteroid is very huge, 12 hours, and our observations are limited to 3 or 4 hours, it's very important to time the observations to get these type of impacts. Like professionals with bigger telescopes definitely won't have any problem getting these impacts. As you can see in the bottom, they're able to get all three mutual impact, all three mutual events, the primary and secondary occultation, as well as the primary eclipse. One more thing I wanted to share is I've also been getting data from the NewSat satellite, and this data, so NewSat is actually our own Canadian space telescope, so it's rotating the Earth constantly, and I was able to get my first set of 30 images. Unfortunately, the SNR, or signal to noise ratio, I was getting is very low, about 15, while the expected, or the desired, is 100. So in the future, I'll be increasing exposure times and changing different factors to be able to get a higher SNR and use this information. Also, the pixel scale is 3 arc seconds per pixel, while the other telescopes I was using normally had around a 0.3 arc seconds per pixel, which gives much better results. But again, by adjusting configuration settings, I will still be able to use the NeoSat telescope to get further observations. And like all my other projects, I always publish my data open source. So I've published my data on the AlcDev database, and here it'll basically all the other previous observations of Didymos from the AlcDev database was before, very long time ago, at around 2003. So I'll be adding my more recent observations to make the database, improve the database. And so I'll also plan to submit my observations to the DART observing group, but they have very strict guidelines. For example, we need 6 hours of observations, and the RMS should be less than 0.01 magnitude. And they have also rules on the exposure time to use, and filters, and so on. I would also like to acknowledge people who have helped me with my project. For example, Christina Thomas, who is a project lead in the DART mission, and she, through Zoom calls, has been helping me learn more about the DART mission and about configuration settings to use. Also, Christian and his team from iTelescope, along with many other people who have helped me get observations, or analyze my observations, or even give me advice on what filters and so on to use. I'm continuing my observations to post-impact. So if anyone has any telescopes, or you're part of any organization that has any telescopes, I'd be really grateful if I could get some observing time on them, so that I can continue my observations. I'll also be presenting at the next Rural RAS meeting next month to talk about my post-impact observations of this asteroid system. So feel free to tune in if you found this presentation interesting. It was great presenting, and I'll be happy to answer any questions if there's any.
Thank you, Arushi, for an amazing project that you shared with us, and congratulations on the results you obtained. Very, very accurate. Well done. We look forward to the next presentation next month. Anya, do we have any questions for Arushi?
Yes, we do. And firstly, I'd like to say, really cool. I definitely want to rewatch this tomorrow and over the weekend. Our first comment is from Eric Briggs, who says, "Great light curve." My question is if any of your steps in how you created this work is available via Jupyter Notebook.
That's a great question. So While some of the parts of my project I've been experimenting using Python, most of my analysis was carried out through a software called Tycho Tracker. So it's a relatively cheaper software, which I found was very useful because I was able to perform all of my steps on it, and it's also a regularly updated software.
Cool. Our next photo is from Sassy Photo. I apologize. Our next question is from Sassy Photo. When combining data with others, did you use the same filter? I'm asking because the phase angle scattering can be different with different filters.
That's definitely a great question, which is why all observations were analyzed separately. So yes, there were some of them were taken through different filters, which is why all of the offsets and applying data was done separately for each observation before combining them together, so that it would all match with the filters and other configuration settings set for that specific observation.
Fantastic. Sassy Photo also says, Bravo Arushi, and thank you for your amazing presentation.
Thanks.
And that's all we have.
Good. Thank you, Anu. And thanks again, Arushi. And we'll see you next month.